Pythagorean identities. The ordered pairs on a circle of radius r satisfy the equation x squared plus y squared equals r squared. The generalized definitions for cosine and sine on a circle of radius r are, so we have, let's see, cosine of t is x over r, and sine of t is y over r. Well, we can solve each of these for x and y respectively. So that would give me x is, multiply r on both sides, r cosine of t. Do the same thing for sine. We get y equals r sine of t. So we can actually take each of these equations, okay, and plug in r cosine of t and r sine of t for x and y up here. So let's see what I get. I get r cosine of t all squared plus r sine of t, right, quantity squared, is the r squared. All right, so what would this work out to be? Well, that would be r squared times cosine of t all squared. So remember, when I'm squaring two things that are multiplied, like a times b squared, I get a squared times b squared. So the result is r squared times cosine of t all squared. Do the same thing with this term, r squared. Oops, coming back to that, sine of t squared equals r squared. And now, because r squared is never equal to 0, we wouldn't have a circle at all, I can divide each term by r squared. When I do that, I get cosine of t all squared plus sine of t all squared equals 1. And we often see that written as cosine squared t plus sine squared of t equals 1. And we call this an identity. An identity means this is true for every angle t. So we're not limited. We're not trying to solve this equation for what t's make this true. This is true for every angle t. Okay, great. So this is one we want to remember. And we can derive two alternative forms of the Pythagorean identity just from this one. So there's actually three, but what I usually do is just memorize this one and then derive the other two quickly. So cosine squared of t plus sine squared of t equals 1. And we have these squares. See how I have cosine squared t, but the 2 is kind of in this funny place here? We do that so that sometimes if we have this 2 appear, the exponent, it can kind of look like I'm just squaring the t unless I put this extra set of parentheses in. It gets a little bulky. So oftentimes mathematicians will just put it here to show that this is this entire quantity being squared instead of just the angle being squared. Okay, so what I'm going to do is write this twice. And so I have cosine squared t plus sine squared t equals 1, and then I've written it again next to it. So I'm going to take the first time I wrote that, and I'm going to divide both sides, both sides, which means every term, by cosine squared t, and see what I get. So when I do that, I get, let's see, this term, the first term becomes 1, sine squared t over cosine squared t. Well, that's just really sine of t over cosine of t all squared equals 1 over cosine of t all squared. So what does that look like? Well, this is 1 plus what's inside here? I recognize that as tan t. So that's where our reciprocal and quotient identities kind of come back. And this is just secant of t all squared. Now, we want to kind of write this in a little bit cleaner way here. So 1 plus tan squared t equals secant squared t. All right, we can do it on the other side. Here we divided every term by cosine squared t. Over here, I'm going to divide every term by sine squared t. That'll work very similarly. So what's my result? Well, cosine squared t over sine squared t. So we can kind of follow this. Sine squared t over cosine squared t gives me tangent squared t. Cosine squared t over sine squared t is going to give me cotangent squared t. Sine squared t over sine squared t, that's just 1, and 1 over sine squared t is going to give me cosecant squared t. So I can use each of these. If I need to use them inside some problem, I usually don't have these memorized. I just derive them quickly from the original Pythagorean identity.